A very good morning to all of you. Today I am going to give you the explanation regarding what is a process. So, what we define a process? Whatever is executing in our system is called as a process. So, whenever anything which is newly created, it is getting executed in our system, it is called as a process. So, we see what can be the part of a process. When a process is created, it is a new process. So, a process is created, now it has to be get executed. So, from a new process, these are the different states of a process. So, we will see what is the process state diagram. Initially, when a process is created, it is going to be a state called as new. So, when a process is created, it is going to the state new. From new, it is moving to the state called as ready. What do we mean by ready? Ready means when a process has been created, it has been shifted to the ready state. Now, our process is ready to be executed. It is just waiting for the CPU to be allocated to a process. So, from ready, we will move to the state called as running. On which condition we are moving from the ready state to running state? When our scheduler or dispatcher is going to send our process from the ready state to running state. In that case, our process is shifting from the ready state to the running state. So, running state, this is the state where at a time it is possible that only one process can be in the running state. What about the ready state? In ready state, there is a possibility that there can be more than one process. So, in the ready state, we also have a ready queue. So, ready queue, what do we mean by a ready queue? Ready queue, here we are having a queue structure in which all the processes which are newly created, which are shifted to the ready state, they are going to be added in the ready queue. And the working of this ready queue is also in the same manner like a first in, first out, P0, P1, P2, P3. So, processes are getting adding from this side, and whichever process is at the first side, the CPU is allocated to the process which is at this end. So, ready queue structure is in the same manner of the processes which are shifting from the new to ready, it is allocated to the queue in the same manner. Then from the queue, the scheduler dispatcher is deciding which process has to be shifted from ready to the running state. In running state, it is always compulsory that only one process will be there in the running state. From running state, it is being moved to the blocked state or terminated state. Terminated state means my process has completed its work or my process has been aborted, its work is completed. In that case, my process is moving from running to terminated. Another possibility is from running, it is moving to the blocked. This condition is when my process is waiting for some input output event, then it is moving from running to blocked. That is the need of a process for some input output event. In that case, process will be moved from running to blocked. When there is an interrupt from the system, my process is getting interrupted by the system, that is when any interrupt is going to occur. In that case, my process will move from running to ready. If any IO event wait is there, in that case process will move from running to block. From block, it is not possible that my process will move directly to running state. Whenever this IO input output event has been completed, the process will move back to ready state. That is, IO event has been completed. For the process which has been requested some input output event, that event has been completed. In that case, my process is moving from blocked state to ready state. It won't move directly from block to running. Again, the process has been moved to ready state. There the process will be allocated to the ready queue depending upon which scheduling algorithm we are using. And from the ready queue, depending upon the process turn, it will be again shifted to the running state whenever the turn of the respective process will arrive. So, this is our 5 state process diagram. So, our respective 5 states are new, ready, running, block, terminated. New, the state when a process has been created, newly created process. From new, it is moving to ready, where it is allocated to a ready queue. From ready queue, it's the responsibility of the scheduler dispatcher to decide which process has to be moved to the running state. From running, it will move either to the block state or it will move to the terminated state. When the working of a process is completed or process is aborted, it will move from running to terminated. Or our process is waiting for some input output event. In that case, the process will move from running to blocked state. From blocked, when the input output event of the respective process has been completed, it will move from blocked to ready. It won't move from blocked to running. And again, the sequence will happen in the same manner. Next is our 7-state process diagram. So 7 state, all these 5 states are going to happen in our main memory. When our main memory is getting full, we want our main memory to be freed. Whenever some process are there which needs to be executed on some priority basis, in that case we have to make our main memory free. So for that case, we are adding 2 more states called as suspended, blocked and suspended ready. These 2 states are going to happen in my secondary memory. The need of these 2 states is I want to free up my main memory for some priority based process. So I am shifting few processes which are in blocked state from blocked state of main memory to suspended blocked in secondary memory. Here they are shifted to suspended blocked. These processes are also waiting for some IO event. Their event has not been completed, so they are shifted from main memory blocked state to secondary memory suspended blocked. From this suspended block state, when their IO event has been completed, they will be shifted to suspended ready. From suspended ready, they are being shifted to the ready state. They are shifted from suspended ready to ready. Again, their working channel is in the same manner. From ready, they will move to running. After finishing, they will go to terminated, or further they need any more IO event, they will move to blocked, or they are interrupted by the system, they will be moved back from running to ready. This was our 7-state process diagram. So we have seen here why the processes are getting moved from ready to running. That is depending upon the scheduler and dispatcher. Now we'll see what are the different kinds of scheduler. We are having 3 different kinds of scheduler: long-term scheduler, short-term scheduler, and mid-term scheduler. Long-term scheduler, these are the scheduler dispatcher which are required to shift our process from secondary memory to main memory. As we have seen in the last time in the 7-state process diagram, that from blocked state we were shifting our few processes to suspended block. We were shifting it to free our main memory. In that case, few processes which were in the secondary memory, when their turn comes, it has to be shifted back to the main memory. So through long-term scheduler, we are shifting our process from secondary memory to main memory. Short-term scheduler, this scheduler is used to shift our process from ready state to running state. That is in the main memory. Our ready state is also in the main memory, our running state is also in the main memory. In ready state, we are having a ready queue. All the processes are placed in the ready queue. Out of that queue, we are going to pick one process and we are shifting it to the running state. That is being decided by the short-term scheduler. Next is mid-term scheduler. The role of mid-term scheduler is to select which process has to be shifted from main memory to secondary memory when it is required to free our main memory. So these are our 3 different kinds of scheduler. I will repeat it again that a long-term scheduler, the purpose of long-term scheduler is to shift a process from secondary memory to main memory. Short-term scheduler, shifting a process within a main memory from ready state to running state. Mid-term scheduler, to shift a process from main memory to secondary memory. This was all regarding the scheduler. Next is our different scheduling algorithms. So, what are the scheduling algorithms? Why this scheduling is required? The role of scheduling is, as we have seen in the state diagram, within the ready state, we are having a queue that is called as a ready queue. In ready queue, so many processes are there. From those processes, a process has to be shifted from ready to running. So, which process has to be shifted from ready to running, that is being decided by the scheduler, and scheduler is deciding it on the basis of the scheduling algorithms. The scheduling algorithms are categorized into two categories: primitive scheduling algorithm and non-primitive scheduling algorithm. So, primitive scheduling algorithm means a process, when it is getting executed, it will be preempted in the midwhile of its execution depending upon the requirement. Non-preemptive scheduling algorithm, once a process has been moved to the running state, means CPU has been allocated to a process, the CPU can't be taken back from that process and can be allocated to another process, that is called as a non-preemptive. In preemptive, once the CPU is allocated, it can be taken back, it can be given to some other process depending upon the requirement. In non-preemptive, once the CPU has been allocated to a process, it can't be taken back, it can't be allocated to any other process. Next, we will see which are the different scheduling algorithms which are being placed as a preemptive scheduling algorithm and non-preemptive scheduling algorithm. Non-preemptive, the very basic scheduling algorithm is first come, first serve. As all of us are aware that how the queue is working, the working of a queue is in the same manner. Whichever process or whichever thing is arriving first in a queue, the CPU is going to be first allocated to it. That is the working of the first come, first serve. Next non-preemptive is SJF non-preemptive. SJF is shortest job first. As in a normal life also, we are having so many jobs to be completed within a span of time. So, on what basis we are deciding that which job has to be done first? The simple scenario is we will try to complete our work which is acquiring less time, we will try to complete that work first. So, that is the simple working SJF non-preemptive. Out of the processes which are to be executed, it is being checked which process requires less execution time, the CPU is allocated to that process first, next the next order process. In this manner, the CPU is allocated to the remaining processes, and this is a non-preemptive. Once the CPU is allocated, it can't get preempted and be allocated to the another process. In preemptive, for SJF only, we are having shortest remaining time next. That is, this is a preemptive SJF scheduling. In this, if a CPU has been allocated to a process which is going to execute for a less span of time, and while its execution, if any new process arrives which require less time compared to the currently executing process, the CPU will be taken back and it will be allocated to the another process. That is a SRTN. SRTN, shortest remaining time next, and it is a preemptive scheduling algorithm. Next preemptive is round robin algorithm. Round robin, it works in a circular queue manner. Whichever processes are there, it's our responsibility to allocate the CPU to all the processes in a defined time manner. So, time quantum is specified there. To all the processes, we are allocating the CPU for this defined span of time, and once the rotation of all the processes completed, the next rotation will start for all the process. If any process in the midwhile is getting completed its work, it will be back out from the queue. Whichever are the remaining processes, their rotation turn will be continued. Next is non-preemptive is priority scheduling. It is also of two kinds, preemptive and non-preemptive. In non-preemptive, on the priority basis, our queue structure is decided. Whichever process is having the higher priority, we are going to allocate the CPU to the respective process. And once the CPU is allocated, it won't be preempted. In preemptive priority, if we have allocated the CPU on the basis of priority, and when a process is getting executed, at the same time, if any new process is arriving which is having the higher priority compared to the currently executing process, the currently executing process will get preempted and the CPU will be allocated to that process. So, these are our different scheduling algorithms, which is categorized as preemptive and non-preemptive. In the next lecture, we will see in detail with an example how these scheduling algorithms are going to